Good morning. My name is Grigory Davrazos, and today I will present our work on active learning for fault diagnosis of inverter-driven permanent magnetic synchronous motors. This work investigates how we can drastically reduce annotation requirements while still maintaining high classification performance. The key idea is that instead of labeling all available data, active learning selects only the most informative samples. First, I will explain our industrial motivation and the problem setup. Then I will present the dataset, methodology, experimental setup, the use active learning strategies, and experimental protocol. After that, I will discuss the main results and practical implications. PSMs are widely used in industrial automation, robotics, electric vehicles because they provide high efficiency. However, failures can cause expensive downtime and safety risks. This creates a strong need for reliable fault diagnosis systems. Supervised machine learning works very well for fault diagnosis, but it requires large amounts of labeled data. Industrial environments, obtaining labels is expensive and time-consuming because experts must inspect or run controlled experiments. The problems becomes even harder in multi-class diagnosis where several fault types must be distinguished from one another. Uh, we formulate the task as a nine classification problem. Each sample is represented by 25 engineered features extracted from electrical and thermal measurements. F0 corresponds to the healthy condition, while F1 and F8 represent faulty conditions. As you can notice, the dataset is imbalanced. For example, the healthy class contains over 4,000 samples, while some fault classes only a few hundred. Let's explain the basic ideas behind pool-based active learning. In pool-based active learning, we begin with a small labeled set L and a large unlabeled pool U. The model is trained on the labeled set. Then an acquisition function scores the unlabeled data according to the informativeness. The most useful samples are selected, labeled, and added back to the training set. To quantify label efficiency, we define a metric that is the percentage of labels we can avoid while still achieving at least 95% of the full budget macro F1. Macro F1 metric is selected here because it gives equal importance to minority fault classes. Next, I will summarize the main contribution of this paper. First, we provide a systematic benchmark of 6 active learning strategies on a 9-class PMSM fault dataset. Second, we evaluated label efficiencies under a stratified 5-fold cross-validation across 10 budget levels from 1% to 100%. Third, we demonstrate that up to 95 or 98% of annotation effort can be saved while maintaining near optimal performance. Finally, we analyze which strategy classifier converts faster and therefore is most suitable for industrial deployment. Now, I will describe the dataset and pre-process pipeline. The dataset contains 10,875 samples and 25 features. The features include electrical measurements and thermal signals. The pre-processing pipeline includes label encoding, missing value imputation, removal of invalid values, and FAO fault stratified sampling. Because the dataset is imbalanced, micro F1 metric was selected as the primary evaluation metric. Next, I will explain the active learning workflow. We begin with a very small labeled samples, only 74 samples corresponding to 1% of the active learning pool is used. The model is trained on this small set. Then the acquisition strategy scores all unlabeled samples. The top ranked samples are queried and added to the label set. This process is repeated iteratively until the target budget is reached. We evaluate performance at several budget checkpoints, ranging from 1% to, to 100%. The goal is to determine how quickly each strategy reaches near optimal performance. In the next slides, we'll present the different query strategies. We use different query strategies that belong to different categories, such as uncertainty-based, committee-based, diversity-based, and hybrid. As baseline strategy, we use random sampling. Our main question is which strategy achieves the best performance with the fewest labels. Now, let's have a look at the classifiers used and the experiments. We focus on tree-based models because they perform well on tabular sets. They are also lightweight, computationally efficient, and explainable. We evaluate decision tree, random forest, gradient boost, and extra trees using scikit-learn library. Now I'll describe the experimental protocol. We use five-fold cross-validation with a fixed random seed for reproducibility. Within each fold, part of the training data is preserved for validation. We evaluate multiple labeling budget levels from 1% to 100%. At each iteration, approximately 74 new jumps are queried. The implementation was built entirely using Python ecosystem. Now we move to the main experimental results. This table shows macroeconometric scores for random forests across different active learning strategies and labeling budgets. The most important result is that QBC vote entropy strategy reaches 90.98% at macro FN1 metric using only the 10% of the labels. This is essentially identical to full budget performance. This means that about 90% of annotations can be avoided without sacrificing accuracy. Another significant result is that committee-based methods clearly dominate for low budgets. The next slides will visualize these trends through learning curves. These learning curves show how macro F1 metrics evolve as the labeling budget increase. Even with only 1% label data, all strategies exceed 91 macro FN metric. Committee-based methods such as QBC and BALD rise much faster in the low budget region. After 40% of the budget, all strategies converge. At that point, the model has already learned most informative regions of the feature space. Similar convergence patterns are observed for, uh, for the rest of tree-based classifiers. This table summarizes the best results achieved by each model strategy combination. Random forest is clearly the strongest base learning, while RF and plus BALD strategy achieves perfect performance. RF plus QBC is more label sufficient because it reaches near perfect performance. So, if our goal is to minimize annotation counts, QBC query method is especially attractive. Committee-based methods are especially effective because they capture disagreement between models. Under class imbalance, they preferentially select minority class boundary web samples. In practice, the experimental workflow is compatible with the predictive maintenance workflow. However, a limitation exists. For, for, for example, this study uses only one of live static dataset. We also assume ideal labeling without annotation noise or delays. The main conclusion is that active learning can drastically reduce annotation requirements for PM SM fault diagnosis. One important point also to remember is that the best performance was achieved not by using more data, but by selecting more informative data. This demonstrates strong potential for real-world industrial application. Future directions include online active learning, deep learning, transfer learning, and human-in-the-loop scenarios. Thank you for your attention. I will be happy to answer any questions.